All right, looks like that's going. So welcome back, everybody. Again, my name's Andrew Harrington, and we're going to pick up where we left off. I'm going to try and go a little bit faster today because I'm behind where I wanted to be. I have a tendency to get kind of distracted as I start talking about this stuff. So today we're going to pick up where we left off, modeling 3 winding transformers. Then we're going to move on to modeling the rest of the equipment that you're going to need to have in your ASPEN OneLiner model or potentially have in your ASPEN OneLiner model. Then we're going to talk about modeling different types of relays and how that works. And then we're going to run some faults and look at how the data is presented in ASPEN OneLiner and different ways of looking at the fault information. And then that'll be it for today. Next week, not next week, Thursday, next class, we'll start talking about how to actually coordinate different relays and looking at their responses to the faults that we're going to run. So I think I got through most of this. One thing I didn't talk about is the different winding configurations. So you can see that for a 3 winding transformer, have a good night. There's a different vector diagram for 3 winding transformers versus 2 winding transformers. This is a YN. These are both capitalized, so that's the high voltage winding, and the N just means that the neutral is available for use. So there's a neutral bushing right there, H0. And then there's a lowercase y and a lowercase n. So that means that there's also a low voltage Y winding with a neutral available. And then 0 means that there's no phase shift between the high voltage winding and the low voltage winding. That's why I said that sometimes it's referred to as 12. It can also be referred to as 0. And then there's a delta tertiary winding with a vector angle of 1, which means that it lags the other two, okay, by 30 degrees. So in ASPEN OneLiner, when you look at a 3 winding transformer, this one happens to be a auto transformer with a delta tertiary, but you have the other options. You can do YY with a delta tertiary, Y delta delta, obviously all the different types of configurations. If your particular transformer test report doesn't provide you with the R and X values, that was something that we talked about and is going to be part of a homework problem, you can calculate the particular R and X values if they give you the load losses and percent %Z. So you're always going to have the percent %Z on the nameplate, and then they'll often give the load losses. And using the load losses and the percent %Z, you can calculate the R value. And if you have, so the Z is at this angle, and then the R is down here, and the X is here. Well, once you know what the Z is, and you can calculate the R using the percent %Z and the load losses, then you can use trigonometry to get the X values. So this series of calculations is going through how to do that. And it's simpler than it sounds at first, because it turns out if you just take the load losses in watts and divide by the MVA rating of the transformer where that load loss was provided. So in this case, we used the high voltage no load tap position of 3, which is the nominal no load tap position, and looked at the base transformer MVA rating of 12. These are the load losses at that tap position and a neutral LTC tap position, and then the base MVA rating of the transformer. You divide those out and you get your R value in per unit. So we were able to get that. And then you can use, like I said, trigonometry to back calculate the x value. Okay, so this is just Pythagorean theorem. I'm sure you guys know how to do that. So if you need an example of how to do that, it's in the slides. I guess that would be it. I think that was all we left out for three winding transformers, and I wanted to cover that example of how to get the R and X values if they're not provided directly in the report like the two winding transformer provided. Okay, modeling generators. So the generators are modeled in OneLiner. That's these little circles here, and then the ones with numbers. This is a Type 3 machine, and then I think there's also a Type 4 machine in here somewhere. Yes, and so that's why those have the 3 and the 4 in them. The one without a number is just a traditional synchronous generator. You model the generator data kind of all at once, and then you can have multiple units on the same bus. And the reason that they do that is so that you don't have, if you have a bus with 4 generators on here, you don't have 4 individual generators. They want you to aggregate those as much as possible. So you model one generator on the bus, and then you model multiple units inside that model of your generator. The internal V-source settings, this is only applicable if you've got the fault options window, which we'll cover before we start running faults. That's what they're going to use if you use the from a linear network solution option in the faults option window. And that's typically what you're going to want for doing coordination studies and fault analysis. And we'll talk about that more when we get there. But that's where this comes into play. And we also talked about during the last class that generator reference angle. You need to set that up correctly. And we talked about how to make sure that the generator that you're modeling has that correct angle. Because if you mess that up when you're using the linear network solution, it's going to incorrectly display your fault currents from the generators. So you want to, and there, like I said, there's no good way of figuring out what your reference angle needs to be, because for a big system, the generator reference angle is assigned in OneLiner. And remember that when you do the check for network anomalies and you do generators with the wrong reference angle, it'll tell you which bus is your reference angle. It's 8 Kansas. Well, if you think about the ISO New England model, which has most of New England's power system in it, this bus may be in New York somewhere, and you're doing a study in Maine, and you don't want to have to trace through all of the phase shifts for every transformer between the bus you're adding your generator on and the reference bus. So that's why this tool is really helpful. You can just, pick 0 and then check to see if the generator that's connected to that you've just modeled has the right reference angle or not, and it'll tell you what the right reference angle is. But you need to make sure that that's set correctly. So that's really important, and it's not obvious if you just look at this parameter. At least I would go, what reference angle? I don't know. What does it need to be? So, okay. Current limits are used or used to be used for Type 3 machines, and they're no longer needed because they now have the ability to model Type 3 machines in OneLiner. So what they used to do is recommend that you set up a generator with a low impedance and then enforce current limits to try to mimic the way that the Type 3 machine would output fault current. So say it was a double induction machine that had a response immediately after the fault of putting out, say, 1.5 per unit of current, which then quickly decays to 1.2 or 1.1, somewhere in that range, fault current. You could set current limit A to that 1.5 per unit current value, and then this to the 1.2 per unit current value. And then later on in the fault options window, you used to be able to enforce one of those current limits, and so that you could consistently model all of your current limited generators the same way. Now you can actually model type 3 machines, so this is no longer absolutely necessary, but it's there for backwards compatibility because a lot of those older ASPEN OneLiner models still have current limited generators in them. So they left it in there, but you shouldn't need it anymore. The power flow regulation options are only if you're using the ASPEN power flow simulation, which is an additional add-on package that you can get for OneLiner, used for power flow studies. We don't need to worry about that. We don't have that option, and at least in my experience, you don't have that option. So once you've kind of set up this data, then you can add your individual units. And so in OneLiner, if you do a new unit or edit this unit, then you get your generating unit info. So now you can put in the nameplate rating of that particular generator, and then the impedances that you can get from the generator manufacturer data. These are your subtransient, transient, synchronous impedances, and then the negative sequence synchronous impedance and the zero sequence synchronous impedance. And I believe you guys have talked about this in previous classes, but the subtransient impedance starts out, well, the current is high, the subtransient impedance is low, and then the amount of current decays over time. So this will come into play later when we talk about the fault options, but you want to keep that in mind, that these impedances are different, and you can get that data from the manufacturer information. And then when you go to run your faults, you can decide, do I want to use the subtransient impedance because I'm looking for my maximum fault current? Or maybe I want to use my synchronous impedance because I've got a time over current element that's going to operate in a couple seconds. And after the subtransient impedance has moved into the synchronous zone, my fault current is going to be lower. And if we just model the fault using the subtransient impedance, you may get a faster relay operate time than you're actually going to experience in the real world. So again, mostly just to let you know that you need to pay attention to these options, and we'll talk about this a little bit more. The neutral impedance, if the generator has a neutral resistor or reactor, you would model that here much the same way you would model the neutral resistor and reactor for a transformer, which we talked about. The scheduled generation, that's again only used for the ASPEN power flow simulation, so we don't need to worry about that. And then the P and Q limits aren't used at all. They've just put that in here for now, so don't worry about that. They may use that in later versions of the software, so they've put it in there, but currently they don't use it. So where do we get the data for modeling the generating units? Similar thing here, we've got some information that you might get from a manufacturer for a particular generator, and this shows the kVA rating of the generator, or MVA rating, 2.5 MVA for this particular unit, the subtransient impedance, the transient impedance, and then the synchronous impedance, negative sequence, zero sequence. And so it gives you those values in per unit on the generator base. And then it also gives you the time constants. So you might look at this and say, okay, well, the subtransient period is about 0.02 seconds. So not very long, right? So again, this is where you'd want to go back and refer to if you had a relay that was operating on something that took a long time, like time over current. If it's operating in a couple seconds, obviously you're not going to want to use the subtransient impedance. Okay, type 3 wind plants. Also known as doubly fed induction generators. These are similar when you look at the generator data window, although it says type 3 wind plant, but you set up the number of units, the MVA rating for each of them. So this would be like if you had 10 wind turbines, there are 10 of them connected to this bus, and each of them has 3.8 MVA rating. Also, you might have the rated megawatts, because they're also capable of putting out VARs. The unit megawatt generation, that's for the power flow option. Yeah, okay. Right. Okay. Yeah, this is the new method of modeling type 3 wind plants that we talked about. The crowbarred option, there's a ASPEN YouTube video that I watched on this a couple of years ago, and it talks a lot about how that option is to simulate faults that are near the terminals of the wind generator. Apparently, if you have a fault that's right on the terminals of the generator, ASPEN OneLiner is not very good at modeling the reaction of the generator for that. So usually you might see fault currents that are in the 1.1 to 1.3 times full load current. But when the fault is very close to the generator terminals, you can get fault currents up to 5 times the full load current. So you don't typically need to worry about this, but you might want to use it if you're trying to size the interrupting ratings of equipment, like a breaker, because if the fault is right at the generator terminal and you can have up to 5 times the rated output of the generator, you want the breaker to be able to clear that. But in most cases where the fault's not right at the generator's terminals, you don't need to worry about it. So that's what that crowbarred selection is for. We'll talk about this when we get to the fault options window, but you have to, if you have type 3 wind plants, you have to make sure that you've got the simulate type 3 wind plant option enabled in your fault options window. So this is what I was looking for. So according to ASPEN, most users can leave the advanced settings. That's this selection here at the defaults. The data that they list in here is basically typically not even available from the manufacturers. It's considered proprietary information. There was a series of tests and studies done by some company in Germany that ASPEN worked with to figure out what typical data was. And that was how they were able to add the type 3 wind plant model to the software. And before that, like I said, they used current limited generators. So if you have this data for your particular wind turbine, I guess by all means, go ahead. Otherwise, you don't have to worry about it. All you really need to worry about is this type 3 wind plant data. So where do you get this data? Another just example of a project I worked on in the past where the ratings of the generators were provided by the equipment manufacturers. So I was able to get, the MVA rating of the generator, the megawatt rating of the generator, etc. And then the maximum short circuit contribution. So this particular generator is 1.45 at peak and then 1.05 per unit continuous. Converter interface resources. So these are solar farms and battery energy storage systems, or also known as type 4 machines. There are a lot of these going in the system right now, as I'm sure you've probably seen them popping up all over the state for those of you that live in Maine. This was also added to the software just a few years ago. So this is relatively new. Again, you have to enable the simulation of converter interface resources in the fault options window. So pay attention to that if you have solar farms or battery storage systems in your model. They also added the ability to, one thing I wanted to talk about here, most of this stuff you can leave at default. And then there's also the slope of the negative sequence dynamic reactive current injection characteristics. It's a real mouthful. Most of the time, this will be 0 in, again, in Germany, where they're doing a lot of this work right now as well. A lot of the manufacturers for this equipment come from Germany. They're starting to add negative sequence current to the inverters for the type 4 solar farms and battery energy storage systems. And this is great for us protection engineers, as I'm sure you'll learn about in the distance protection lectures. The negative sequence current is really important for determining fault direction. So a lot of times the directional elements, if the source behind you has a lot of type 4 machines, I guess you'd call them, you don't have a negative sequence source behind you, and so you can't use directionality unless the fault is towards the solar farm. So they're starting to add this option. You probably, at least for the next few years, you probably won't have to worry about this. But in the future, hopefully we're seeing more and more negative sequence dynamic reactive current injection characteristics. And I talk about that here. Let's see. Resource shutdown. This is something that I've run into a few times where it's caused me issues. Things have been a little tricky because this resource shutdown option, if the phase voltage gets above 1.2 or drops below 0, then if you don't pay attention to what these settings are, you might find that the inverters don't put out any fault current. So I don't remember what the default is, but there have been times where I'm running faults near a solar farm, and all of a sudden I look and I go, whoa, that's not putting out any fault current at all. Oh, well, it's because the voltage at the terminal of the type 4 machine is below this value. So I have to go back, and then if I want to see what it would put out, assuming that the inverter didn't shut down due to loss of voltage, I have to lower this and see what it's actually going to contribute to a particular fault scenario. So kind of paying attention to those. But this stuff is all based on your particular inverter. You just have to get the data from the manufacturer. So this is another example of information that I received for an inverter that I had to model. So I just included that for your reference. Modeling shunts. So ASPEN OneLiner refers to shunt capacitor and reactor banks just as shunts. So when you're modeling either one, like if you had to add a capacitor bank to a bus, and you wouldn't see the option to add a new capacitor. So you might be kind of confused by that. Well, they just call it a shunt. When you add the shunt, there's actually a really cool tool here. You just go over this convert button. You put in the megawatt rating. If there's some resistance to it, most of the time it's just either a straight capacitor or reactor, and you just put in the number, the MVAR rating for the capacitor or reactor. If it's a reactor, you put in a positive value. If it's a capacitor, you put in a negative value, and you just say convert, and then it'll automatically calculate your shunt susceptance for you. And then that's it. Boom. So modeling capacitor and reactor banks are pretty simple. They also don't put out any fault current, so they don't make a big impact to your coordination studies. So we're not going to spend a lot of time on them. Yeah, so I just want to touch on this briefly. Use the convert button, like I just showed. That's super convenient. And then this is something good to know. If the shunt is ungrounded, you put in a G0 and a B0 value of 0. And if it is grounded, you just set them equal to the B value. Okay. And then the G values are only used for like dynamic VAR systems. So DVARs, StatComs, things that have the ability to also do resistance or do dynamic VAR support. So if you need those, just look at the help files and it'll walk you through it. Not super common. And again, they don't have a big impact on your coordination study because they're passive devices. So modeling relay groups. So relay groups are what are used to model any protective device. So if you want to model a relay or a fuse or whatever, you first have to model a relay group, and that shows up on your one line. It looks like a breaker. So this is a relay group, and the location of the relay group is kind of important to keep in mind. So this relay group in a traditional or typical scenario would represent the high side protection for this transformer. So either a fuse or a breaker. And then once you open up the relay group, then you can model the individual protection elements in that relay group. So this is providing a high voltage 51N, a high voltage 51Q, and a high voltage 51P. So these are time over current elements. It's got a neutral, a negative sequence, and a phase over current element. So to model a relay group, you just click the element near where you want the relay group, and you can right click and just do a new relay group. So the relay groups are pretty easy to add, but then they have their own data associated with the relay group. The types of protective devices that you can add in a relay group is pretty extensive. You can do overcurrent ground relays, phase relays, distance, DS, distance, ground relays, distance phase relays. fuses, reclosers, differential relays. This is line differential relays, not transformer differential relays or bus differential relays, unfortunately. Can't model those, but you can do line differential relays and voltage relays. So your options in this window, you can add a relay, which is right here. You can import a relay. This is a really cool tool. I don't use this enough. If you add a phase distance relay, say, you select from a drop-down menu of all of the different types of relays that are already included in the database files included in ASPEN OneLiner. You can add your own if you'd like. Usually they've got it or something close enough that it doesn't matter. But let's say you want to add a 411 relay. Now you've got to go and manually input all of these settings that are from the relay settings file. So you'd have to open up the relay settings file and then find the Z1 mag setting and then put it in here. And obviously you can see that there's an opportunity for a data entry issue there. And if you enter bad data and then do a coordination study on it, it's not going to, or potentially can cause problems later on, like we talked about. So the import tool, instead, you can import from like a GE settings file or an SEL accelerator database. So here I put one on my desktop. I forgot to do this last year, but I just picked a relay settings file. And now it'll give you the relay manufacturer, type, the model number, firmware version, all of this. And then if you hit next, it'll actually read the settings file and then look at the different types of elements that the relay is using. So it recognizes that there is a distance, phase distance element in this relay. Also, there are ground overcurrent elements. And so this is really cool. So you can hit OK, and now it automatically went and found all of those settings in the relay settings file. And now you've well, first of all, you saved yourself a lot of time, and then you've drastically reduced the opportunity for manual data entry errors. So now I can just say OK for all these, and now it's imported all of those settings, and you can rename them to whatever you like. And I guess I would caution with the use of this, you'd still, or at least I would still want to check each of these manually, because that's just kind of the way I am. But also, there may be something that you're doing in the relay that the import tool misinterprets. So, for instance, if your distance relay has a pilot scheme, and the zone 2 element is used in the pilot scheme, and it's not directly in the trip equation, this relay may not recognize that zone 2 element is not a tripping element. So you might want to say that the signal only zones are zone 2, right? This particular relay, the phase overcurrent element is actually part of the distance relay. So this is the phase overcurrent element. It imported, I'm sure it imported all of these settings correctly, but it's not set up the way that I would do it. I would use this zone 2 supervision option. So what this is when you model a, certain customers, certain clients, utilities, they have phase overcurrent elements that are torque controlled by a distance relay. And the idea behind that is if you want to set a phase overcurrent element with a kind of a sensitive pickup, because the line is long and the potential for fault current being low at the end of the line is there, but you don't want to limit the amount of load that you put on the line, you can supervise that phase over current element with a distance element so that it only operates if the current is above the pickup and you're within the zone 2 reach of the relay. So that this particular relay is for Central Maine Power Company and their 34.5 kV system. That's how they do phase over current protection. So I would model that phase over current relay here using the zone 2 supervision field. And then you can go and select your curve shape and put in the settings for that phase over current element. And now the torque control will be properly applied when you check the operation for faults. And we'll talk about that more when we talk about modeling distance relays. But again, I get distracted. So back to relay groups. That's the import tool. The point I was making was still check the imported data just to make sure that it's imported it correctly, because it may not understand how the relay is supposed to be modeled 100%. The place relay option, that's if you copy. A lot of times you might do a coordination study with a bunch of existing relay settings for an area, right? And you might have to make a change to one. Well, you don't really want to change the relay that you're working on, because you may want to go back to those settings or compare what the new setting is to the setting that was before. If you copy a relay and then paste it, well, now you've got this little tilde at the front to show that it's a copy and paste of the other one, and now you can mess with this one. I guess that's the paste button. The place relay, I don't really use that option. To be quite honest, I've forgotten what that option does. I don't ever use it, so I guess we'll just skip it. Copy and paste is what I was showing. So you can copy one relay and you can copy between relay groups. Excuse me. You can actually copy entire relay groups from one spot to another. So you can copy these and paste them over there. So it added 5 new devices. So now all of those are in there as well. Pretty, I guess, intuitive copy and paste function for Windows-based software. The breaker operation time, this isn't strictly necessary, but sometimes you may want to have that in there. I'm starting to see more clients use this to keep track of their breaker data for particular applications. The interrupting time is, the interrupting time of the breaker, self-explanatory. The trip logic, this is what you want ASPEN OneLiner to use for what device is tripping that relay group. I don't know if I'm saying that well, but basically, usually it's just the fastest device in the group, because all of the relays are looking at the same values, same currents and potentials, and you want to just trip based on which relay operated the fastest, because that's when the actual breaker would open. You can also keep track of your reclosing intervals if you have them. And then again, you can look at different logic options for when you reclose. So you may not want to reclose under certain fault conditions for whatever reason. The trip logic, you saw that in the drop down for both of these. Right now, there's only one option. The other options come into play when you use this protection logic and communication schemes. I rarely use this window, but they are available. The logic schemes would be basically you can add custom logic. Maybe you want to do a DTT scheme so that if another breaker opens in the simulation, that it'll come here and trip this. So you can use like and or gates and stuff like that to set up a logic scheme. You can set up pilot communications channels, so you can do like pot schemes or whatever, like pot, DCB, all the typical pilot communication channels can be modeled. Coordination pairs. This is a handy tool that again, I don't use enough. But what this is for is, let's say, because we're right here, we'll look at these two relay groups. If you have a fault on this transformer, you'd want this relay group to clear that fault, because that'll isolate the transformer, and you want to isolate the minimum number of pieces of equipment and as close to the fault as possible, right? So we want that to operate first. But if that doesn't operate, maybe there's no breaker failure protection in that particular relay group or breaker. This relay hopefully sees that fault, and a relay down here at Vermont would hopefully see that fault, and then these would trip on some sort of time delay should that breaker fail to open. This is kind of the essence of coordination studies, right? We want to make sure that this operates before this, but this will operate if it needs to back up this device. Okay, that's the essence of what we're doing when we do a coordination study. So the coordinations pairs would be to automatically set those up in OneLiner. So you can say that this relay group backs up Montana 33 kV to MT MV bus A. Okay, great. So now this relay group backs up this relay group. And then when you're doing your coordination study, you can quickly add those coordination pairs. And then there are also more advanced tools that I haven't gotten into, but you can run macros in the software to check a coordination for all relay groups that are set up this way. And I've seen a couple of utilities that are starting to move this way to try and automate that coordination process. So I haven't played around with it too much, but it's going to happen more and more, I'm sure, as we try to automate this stuff. So those are the options for the relay groups. We just talked about all the logic schemes you can do. Again, none of this is necessary, nice to have features in some applications. So modeling relays, we're going to go through the different types of relays that you can model. Briefly talk about each of them and kind of some of the different lingo that is used, just to cover it enough so that you know what these different parameters mean. I'm sure all of this will be covered in more detail for the line protection lectures and the transformer protection lectures, but just to give you enough so that you know what's being referred to by ASPEN OneLiner when you have to model the relays. So overcurrent relays are just relays that when the current gets above a desired set point, the relay should trip a breaker or other protective device, circuit switch or what have you. The pickup is the value above which you want the relay to operate for. The curve is the relationship between the current and the time to trip, and it's typically a log scale. I'm sure you've seen or will see the log graphs. That's usually the way it is. There are also instantaneous overcurrent elements. There are other types of ways that you can model it, but usually they're logarithmic, because you can do like voltage controlled or voltage restrained overcurrent elements, but this is most common. The tap unit is really there for older electromechanical relays where the pickup is kind of defined by which tap you're on. It's a physical screw that you would take out and remove. But usually you just use the pickup. This doesn't need to be modeled. If you leave that blank, everything will be fine. It's more for informational purposes. The time dial impacts the multipliers for the log arithmetic equation for your curve. So if you have an overcurrent curve, I don't know if this is mirrored, if I'm doing this the right way or not, but the pickup has the tendency to move the curve left and right. Okay, because the current is on the x-axis. So if you increase the amount of current for the relay to operate, it'll move further this way on the x-axis. And if you decrease it, it'll move this way. The time dial moves the curve up and down. Okay, so that's the way. I think it's the simplest way to really understand what's going on with the time dial. It's just moving that curve up and down, and because it's a logarithmic equation, it's not, a small increase in the time dial may result in a large increase or decrease in the operate time, but ultimately what you're doing is just moving it up and down, and then the pickup moves it left and right. The time adder would be if you wanted to add a fixed time delay to your curve. So I very rarely see that used. There are some applications where they add like a fixed time delay down at the bottom, but usually you don't have to worry about it. But what it does is it just changes. If it was going to operate in 1 second and you had a 0.1 time adder, it's going to operate in 1.1. Same thing for 2. So it actually changes the slope of your curve slightly because the slope is on a log arithmetic scale, and this is adding a linear time delay. So it changes the slope of the curve a little bit. The time multiplier is just what it sounds like. So if you do a multiplier of 1, it'll operate on the curve. If you do 1.1, the time delay will be 1.1 times what it would have been on the curve. Again, these aren't really used very often. The directional control element, this is important. Need to know about this. This enables directionality for the relay. So if the overcurrent element is directional, you have to turn this on, and then you say what the polarizing quantities are, and that depends on the model of your overcurrent relay and or the settings that are in it. So you'd have to look that up for your particular relay. If the relay has the ability to change the polarizing settings, then those are listed here, and you want to enter those per how you're setting the relay. I said earlier that the location of the relay group matters, and it does, because anything that you model in this relay group, forward is considered towards the protected element, and then reverse is towards the bus. So you can get into situations where if you put the relay group here, well, the relay is actually wired with CTs that have the polarity connected opposite, and the software doesn't know that. They don't know that you've got the CTs wired backwards. So if you put the relay here and then just set up all your overcurrent elements the way that they're set, well, it's not going to operate the way that you it actually will in real life because the CTs are wired backwards. So I've seen and gotten into situations where I needed to kind of trick the software. Maybe you add like a short impedance with another bus here and add the relay group in a spot that is totally unintuitive, but it mimics the way that the software expects the CTs to be wired. So keep an eye out for that. And again, that's another reason why when you import relay settings, you still want to go through the actual application, the actual settings, the drawings, and make sure that the settings have been imported appropriately. Okay. The overcurrent relay curve selector. I showed that earlier. But when you model an overcurrent relay and you go to select the curve, you select from the library, and there are all sorts of different manufacturers and relay types in here. So you can go down to SEL relays and select, you know, the 411 U3 curve, and then it'll list. Typically, some don't, but they'll usually list the actual equation that's used to create that curve. They'll say where they got it from and when it was created. And then it'll also give you the path for that library that has that curve. And you can add your own curves if you want. If they don't have it, you can also contact ASPEN, and they're usually very good about this, but they might add the curve for you. They like to do that, at least I think they like to do that, because then they've got the curve in their library and they now can include it for other people to use in future releases of the software. So, but if you want, you can create it yourself. We're not going to go over how to do that, but just know that that's a possibility if you run into a situation where your curve isn't included in the software. Yep. Okay. Custom relay curves. ASPEN OneLiner includes a wide variety of commonly used relay manufacturers and types. You may need to add your own curve. You can use the curve editor. I did go over, I included in the slides kind of how to do that. Again, not going to cover that in depth. Just want you to know that you can do it. Okay, modeling distance relays. Let me check the time. Okay, I've been going for 50 minutes. Modeling distance relays. Distance relays are are used to trip when the measured impedance is less than desired. So say you have a line that's 10 ohms, has an impedance of 10 ohms. You can imagine that if you put an infinite load at the other end of the line and you were measuring the impedance from this end. So you had 10 ohms of impedance, and then out there you've got the load of the system, and you know that load isn't going to be infinite, obviously. But if it were, you would still measure 10 ohms because you need to measure the impedance of the line. So if the relay ever measured an impedance that was less than 10 ohms, you would know that that's due to a fault. Something has happened, because you shouldn't ever measure an impedance that's less than 10 ohms. So that's high level, super simplified explanation of what a distance relay is and is doing. So in that situation, you have the zone 1 reach is an underreaching element. You might set it for 80% of the line impedance, so that if the relay measures an impedance of 8 ohms or less, you know that the fault is on the line. The reason that you set it for 80% of the line impedance is you don't want it to trip for faults that are beyond the end of the line, at least not right away, because you want to let other protection clear that fault typically. So you set it to 80%, of the line-ish to give yourself some margin, because there's relaying inaccuracies, there's CT inaccuracies, PT inaccuracies, ASPEN OneLiner modeling inaccuracies, transmission line modeling inaccuracies. All of these inaccuracies, you kind of try and account for that, and you give yourself a 20% impedance margin, somewhere in that vicinity. But that your distance relay also wants to cover that last 20% of the transmission line impedance. So usually you also have a zone 2 that reaches beyond the end of the line. That might be set at 120 or 150% of the line impedance to make sure that you're covering the entire length of the line, but you put a time delay on it. And that allows the relaying at the remote end of the line to trip for that fault. You may also use that, and I don't know if you've already covered distance protection or will in the future this year, but you might also use that element as part of a pilot scheme, POT, DCB, what have you. And you might have a zone 3 reach that is looking behind you and providing a block as part of that pilot scheme. So there's a zone 3 reach option. And then a zone 4 may be used if the zone 2 and zone 3 are used as part of a pilot scheme, because now you still want to have that, quote unquote, traditional zone 2, which is the overreaching element on a time delay to provide protection for the last 20% of the line, say, that isn't covered by the zone 1 element. And then the zone 2 supervision, we've already talked about that, and that's torque controlling the phase over current element. Okay. Fuses. You can also model fuses in ASPEN OneLiner in the relay group. They're most commonly used to protect the high sides of transformers. They can also be used to protect distribution circuits. ASPEN OneLiner isn't a great software for modeling distribution systems. They can't do single phase faults. Well, they can do single phase faults, but there's no single phase system modeling. Everything's 3-phase. So if you have single phase distribution circuits, you can't model those in ASPEN OneLiner. So it's not commonly used. SIME is another software that you more commonly see for distribution protection. So in ASPEN OneLiner, you're most commonly using fuses to protect transformers. The curves are based on the manufacturer's data for the selected fuse. In my experience, usually the fuse is kind of pre-selected. They have standard fuses that they use for their different transformers. But if you had to select one, you can go through and look at the different curves and see which one protects your transformer the best. Usually you still verify that the fuse protects your particular transformer, but typically the utilities have kind of standard MVA ratings and impedance values that they use over and over again. So they commonly say, okay, well, for a 5 MVA transformer, we use this fuse type, and they kind of standardize on that because it helps them with their distribution coordination and their other protection coordination for the transmission lines as well. So usually you just have to go and find your particular make and model, and then the continuous current rating for that curve, for that fuse. So this particular fuse that I modeled here in the example is a 176 curve. So it's an S&C very slow fuse. The 19 is here. So this is the TCC, the time current curve number. For I think this was a 130 kV. It's in the model. It's the Arizona transformer that I added this to. I think it's 130 kV. And so I selected that TCC number because it corresponded to my voltage rating, and then a 100 amp fuse. So that last 3 digits is for the continuous current rating for the fuse. The current divider option is used if you've got multiple fuses in parallel. They may do that to get the same curve shape, but they can't get say the maximum rating is 200 amps, but they want a 400 amp fuse. You can just put two in parallel. The minimum melt multiplier, this is used, we'll talk about this more when we talk about transformer protection. But this is where you'd enter your multiplier to account for preheating of the fuse. So say you have a distribution transformer that's fused on the high side and there's a recloser on the low side. You're over the life of that transformer, there are going to be a lot of faults on the distribution circuit. Some of them will be permanent, some of them will be temporary. When you have a distribution fault, you'll often reclose the recloser multiple times to see if the fault is temporary or permanent. And if it's temporary, you can restore power to the customers. And if it's permanent, then you want to trip and send somebody out to fix it. When you have those faults on the distribution system, the fuse, obviously it melts when it gets hot, right? So you're exposing that fuse to higher than normal current multiple times through that reclosing sequence, right? So if you just compare the curve of the fuse to the curve of the recloser, you're not accounting for the fact that that fuse is heating up, and as you hit it more and more times, really the curves should be getting closer and closer because it's already hot. So this value, I'm pointing like you can see, but I guess you can see my mouse. So this value is used to account for that preheating, and we'll talk about that more when we talk about transformer protection, like I said. The compute time using total clear versus minimum melt. This is important. When the fuse curves, where did I model that? Arizona. Right here. Okay. If I show the curve for the fuse, you can see it's not one discrete line. It's actually two lines that are closed in by a hatched area. And so the fuse obviously isn't a totally precise element. So it can actually blow at any time within this hatched area. So the lower bound or lower curve is called the minimum melt curve, and that's the published amount of time that this curve could possibly blow for each amount of fault current, right? So this is the minimum amount of time it would take for this curve to blow. It will always take more time than this. And then the total clear is the maximum amount of time that it'll blow at that current level. So these are published curves, and that's to give you that range of time for which this can operate. So you can, I don't know why it's doing that, but when you're comparing to something that's downstream, like in that previous example where you might have a recloser curve down here, you want to make sure that the minimum melt is slower than the recloser, so that the fuse never blows when the recloser should be tripping. But if you were coordinating with something that was upstream, you'd want to look at the total clear time, because you want the fuse to blow before the upstream relay. So that's why you have that option. So you can change it to total clear, and then for a particular fault, let's say you have a close-in fault here. It'll give you the operate time when you show the fault. Okay. The total clear time is 0.126 seconds. If I change that to the minimum melt, it'll say that the minimum melt time is 0.057 seconds for that fault. So the fuse will blow somewhere in there. So that's why you change this back and forth, because when you're comparing the two times, you want to make sure you're using the right value. Okay, how much time do I have left here? Looks like about 10 minutes. Modeling reclosers. Reclosers are pieces of equipment that are similar to a breaker, but they're typically used on the distribution system. They're cheaper and smaller than a breaker, and they usually have lower continuous and interrupting ratings than a breaker. Um, they're usually paired with what they call a recloser controller as opposed to a relay. It's essentially a relay, but they call it a recloser controller for whatever reason. But that recloser controller is probably because it controls a relay, but controls a recloser. That recloser controller is usually mounted in like a weather tight box that'll sit on the pole somewhere, so that you don't need a whole control house, and you can put them out on the distribution system and put them remote to the substation. You don't need additional equipment like a battery. They'll usually have their own power supply that is tapped up to the distribution circuit to power itself. It might have a backup battery in case the distribution circuit is down for some amount of time, so that the recloser controller can still be powered. Usually the trip and close coils or capacitors, depending on the recloser type, are powered from the distribution circuit. They're self-powered, so again, that you don't need an external battery. So those are reclosers. The software has a recloser model that's separate from a relay, and it's meant to be used for recloser controllers. In here, you put in the reclosing intervals. These are the number of seconds between reclose attempts. The total operations to lockout, so that's the number of attempts that the recloser will, well, the number of times it'll operate before it gives up trying to reclose. So that's why it's 4, even though there are only 3 reclose attempts. So it'll operate 4 times and then lock out. The number of fast operations, this is usually used in conjunction with like a fuse saving scheme. And so what I mean by that, and we'll talk about this more when we get to transformer protection, but you might have a fast curve and a slow curve in the recloser. And the reason that you do that is you might have a fault down a tapped single phase distribution circuit that only feeds one or a few houses. And if you have a fault on that circuit, obviously you don't want to take down the whole circuit for that. Well, you might want to take it down temporarily because there's a chance that the fault is temporary. So if you have a fault beyond that fuse, you have some fast curves that are set up to operate before that fuse blows. Okay. Take a couple of attempts, in this case, number of fast operations 2. Try to reclose at least once. And then now we've decided that the fault is probably permanent. And so now we use a slower curve that's slower than that tapped fuse to give that tapped fuse an opportunity to blow and then hopefully keep the rest of the customers online. Super simple, abbreviated introduction to distribution coordination, but that's it in kind of a nutshell. And that's the reason you have this option. Rated momentary amps is not necessary. Again, it's for information purposes only. The interrupting time, again, you might want to know how long it takes that recloser to operate, and sometimes you might want to add that to your operate time for your your recloser to account for the time it takes for the recloser to open. It's most recloser controllers have two units, a phase and a ground. You have a higher one for phase faults because you want to allow as much loading for the circuit as you can, and you might have a more sensitive ground unit to clear high impedance faults like trees. So usually you have a phase and a ground, and then you would specify the fast curve and the slow curve using that same drop-down menu that you use for overcurrent relays. So drop that down, then go and select your curve. And then you put in the pickup and the time multiplier. There's not usually a time dial with reclosers. It's usually just the time multiplier. When you select each of these selections here, I don't know what you call that, these little buttons, this operates in a similar manner to the minimum melt versus total clear buttons for the fuse. So this just shows you which time is going to be shown on the coordination curve, okay, whether or not you want to look at the fast or the slow. Same reason you'd want to look at one versus the other. You're trying to make sure that your worst case scenario upstream coordinates with the slow, and your worst case scenario downstream coordinates with the fast. Okay. Yep. I think I have like 5 minutes. I'm too slow again. Okay, we're not going to get to running faults today. I'll try and just speed through the rest of modeling different relays, and then we'll start on Thursday. We'll start going over how to run faults, and we'll start looking at some coordination scenarios. The rest of these different types of relays are frankly a lot less commonly used. The first one is line differential relays. You can model them. I never actually have, because usually you just, if it's a line diff relay, you can look at the minimum and maximum fault currents and ensure that your line differential scheme is going to operate the way that it should. And you don't really need to model that in OneLiner to check coordination, because it doesn't really need, there's no risk of it overreaching and needing to coordinate with something else. And you know that there's a line diff scheme on there, so you can effectively ignore it if the fault's on that line, because you have the line current diff scheme. So that's why it doesn't typically get modeled. You might want to model it if you're using some of those more advanced tools where we're talking about automatically checking different fault scenarios, because if you do have a line diff scheme, you want to be able to take credit for it in some of those automatic fault checks, but not used very often. But you can potentially add it if you'd like. And this slide goes over how to do that. I don't think we have time to talk about this, so I think I'm just going to skip it. Voltage relays, pretty easy to model. The operate on voltage tab, this is really the only thing you kind of want to know about adding voltage relays. You can select different voltage quantities to operate on, whether it's phase to neutral, phase to phase, positive, zero, negative sequence, or even particular phase voltage values. Set your PT ratio, and then set whether it's inverse time. I don't know of any applications where there's an inverse time voltage element. I haven't seen that before, but it's definite time. You set up what the pickup value is and the delay, and now you can look at the response of your voltage element for different faults and see if it'll trip. You can kind of do that anyway by just looking at the fault values, but you may want to model it for whatever reason. So it is an option. Okay. And with that, like I said, I think I'm out of time. So we will pick up on running faults, and then we'll run some faults and see how the relays operate for them. So thank you for your time. Again, reach out with any questions. I'm not sure if Paul has shared the homework with you yet, but if there are any questions on that, feel free to reach out, or really anything else. Okay, guys, thanks. Bye.